Hi, good morning, everybody. Can you hear me? Okay. Welcome here. Thanks a lot for making it to the tutorial. Between the weather and the early morning scheduling, we thought that we'll be talking to blank audience here. So we recognize your interest and thanks for coming here. So my name is Sharathchandra, Karthik Nandakumar, and Nalini Ratha. He's online, attending remotely. We three have found that this is an interesting topic of intersection blockchain and computer vision, and we'll be roughly presenting for about 90 minutes and taking a break, and then another 90 minutes. About 10 o'clock there will be coffee. So we thought that we'll start with a interesting video which is very relevant from YouTube, and then maybe a couple of minutes of more motivation. After that, there will be outline the technical details of the blockchain, followed by some applications of computer vision. So that's the rough agenda. It can be very interactive. Please feel free to interrupt us anytime so that we can keep this very live. So without that,
artificial intelligence, aka what happens when we take the two hottest technologies of today, AI and blockchain, and put them together, right? Just sprinkle everything on top of each other, right? So let's get right on into this. We've got a lot to cover. So, machine learning, AI, this has been around since the 50s. It's not a new technology. It's a pretty old technology. But basically, the idea has always been the same. We have some data set, right? Some input data set. And we have some objective. We have something that we want the AI to do. In this case, classify a car. Is it a car or is it not a car? So what we do is we feed this AI a bunch of images of cars. So think of it like an Excel spreadsheet with two columns. In column 1, you just have pictures of cars. In column 2, you just have labels. Car, right? And so the idea is that the AI learns the mapping, the relationship between the input data and the output labels. There is some relationship between everything. There is a function in life for everything. But that's a bit of a tangent. The idea, though, is that the human would have to extract all the features of what it means to be a car, right? This is kind of what a car looks like. This is the shape of a car. This is what the exhaust pipe looks like. And this was a very tiring process. But this is what humans had to do. We'd extract features by hand. And so what happened is, once we'd extracted those features, we would feed it to some kind of machine learning model, and there's a lot out there. Eventually, it would learn the mapping, and then give it a new car picture, and it would know, hey, this is a car. But a few years ago, there was a scientist who said, let me take one specific machine learning model called a neural network, enter, drop the beat, right, drop the mic, and feed it lots of data and lots of computing power, and add a lot of layers, deep layers, aka deep learning. That's what we call it. What happened is, when we did this, it started outperforming every other machine learning model. And now, deep learning is the hottest topic in machine learning. It is outperforming everything else. Self-driving cars, drug discovery, everything hot that you're hearing about AI is coming from deep learning, okay? So that was my one-slide overview of AI. So now, blockchain, right? So a couple years ago, there was a programmer who no one knows, named Satoshi Nakamoto, who released a paper on a cryptography mailing list detailing a system called Bitcoin that allows two people to transmit value online without needing a third party, namely a bank. So what happens is, instead of a bank being the third party, there are a group of people called miners, and anybody can become a miner. You just need a laptop, right? Anybody can become a miner. And the idea is that when I transmit value to you from me, these miners have to approve this transaction. They have to say, okay, let me check this list of transactions. So every miner has a copy of every transaction that has occurred in the network. And they have to approve whether or not this transaction is valid or not, right? Because they have the list. So you might be thinking, wait a second, couldn't someone just create a bunch of accounts and say, hey, I'm the majority of the miners, because the majority of the miners have to approve a transaction for it to be added to this list of transactions? Well, no, because Satoshi said every single miner has to prove that they have solved some random mathematical problem. It's called the proof of work algorithm. And that means that you have to have more computing power than the 500 fastest supercomputers in the world combined to have the majority of the computing power in the Bitcoin network. And because no one has that much computing power, no one's been able to hack Bitcoin. And that's why it has a over 100 billion market cap as of yesterday, more than the GDP of some countries, and no one's been able to hack it. It's been around for a decade. It's a really powerful technology. Let's keep going here. But the really, really interesting part about Bitcoin is not the actual application, but the underlying data structure of Bitcoin. So this is kind of a rough diagram of what it looks like, very simplified. But the idea is that we have some list of transactions, right? I'm talking about this list of transactions that all of the miners are holding. And we group these transactions together into little groups that we call blocks. And each block points to the next block. So one block is like, okay, I'm a list of transactions, here's the next block. And the next block's like, oh, thanks for that. Okay, here's the list on the next block, right? And it becomes this kind of chain of blocks, aka blockchain, right? So it's a blockchain. That's what we call this data structure. And because of the proof of work algorithm, no one can modify it. It's an unalterable, immutable in computer science terms. Shout out to all the programmers out there. It's an immutable data structure that no one owns. And this is a very powerful idea. So I like to call this the yin and the yang of AI and blockchain, right? These two technologies go really well together, but no one's really put them together yet. So this is a very futuristic thing. So the yin is AI. AI is probabilistic. It's all about computing the likelihood that something will happen, the prediction of the future, using what it's learned. And an AI is always changing. It's updating its weights. It's learning about the future. And an AI is a set of algorithms that guess at reality. The yang part are blockchains. Blockchains are not probabilistic. They are deterministic. You know exactly what's going to happen, right? They are permanent. They are unchangeable. And they are algorithms and cryptography to record reality. So these two things can go really well together if you break them down into what they're really good at. So we live in a world where we are all using these services, right? And these services collect and monetize our data. That's the business model. But this is a problem because our data is the most valuable thing we have, and it will become more valuable as everything is slowly automated. Your data will be the only agency that you have. It will be your most valuable asset. So you need to own it. But right now, we're giving it away for free in return for a free service. Ideally, these services would be paying us for our data, right? But that's just not the case right now. We need to redo all of these apps that we have in Web 2.0, everything from eBay to Uber to Lyft, all of it, Facebook, right? Morally speaking, this is a terrible idea to let some humans control our data. In the case of Facebook, they modified the newsfeed to affect large swaths of the populace. And the 2016 political elections, for example, in the US, it's just very corrupt. It's just not a good system. And not even talking about it morally speaking, let's talk about it technically speaking. Centralized systems are not good. Take the case of a self-driving car network. Let's say we've got 3 self-driving cars at an intersection, okay? 3 of them at an intersection. And they're trying to decide who has the right of way. But if there was one central server that they all had to talk to 1,000,000 miles or kilometers away, then it would take forever, and there would probably be an accident. Ideally, these cars could talk to each other without needing a third party or a central service or a server. So both technically speaking and morally speaking, creating what are called decentralized applications is a really good idea, and it's what we call as developers Web 3.0, and that's what's happening now. If you're looking for something to disrupt, you take blockchain, you take AI, you combine them together, and you create apps that have never before been possible, and that's the most exciting thing these days.
So from the video you got as much that we are the world here, and it is being sensed. We generate data. We have models, and all of this can be improved in terms of various operations such as safety, sales, in various applications. But there is growing requirements about whether the accuracy, throughput, integrity, confidentiality. So all of these things we want to democratize. That's what the main point of the video there was. So I'll skip this slide. And you got this also from the previous video that we want to, whatever is happening in the world, we want to make a credible ledger out of that in terms of either the transactions or the agreements that have been previously agreed by various stakeholders. Um, so, and the main point of the video was that, instead of each person, each stakeholder having a separate ledger, which is not only inefficient, expensive, and vulnerable, it is not to be very trusted. What we want to do is that create a distributed ledger that can be based on consensus, which can tell who did what, which is immutable, and which is final. So again, we saw that Bitcoin, and the last part of the particular workshop is going to be about 4 main applications of modeling. Modeling people, which is the identity management, modeling the objects, which is the physical world, modeling the models themselves, which is the inference management, and then modeling the content. So those are the 4 pieces we are going to talk about in the applications section. But next, we are going to go, so this is the basic outline of how the blockchains really work, and then the second part is going to be the applications of blockchain for computer vision. Maybe here anybody has any questions or want to interject? Okay,
Okay, so the first half of the tutorial is going to cover the introduction to blockchain, like what is blockchain, what are the algorithms which is driving the blockchain scenario, basically the consensus algorithms, and kind of give some glimpse into different implementations of blockchain. And then the second part, as Sharath mentioned, we'll talk about the applications of how we can use blockchain in computer vision. Okay, so you've already seen the video. So what is blockchain? It's basically the shared distributed ledger, which all the parties try to kind of have the same ledger. So the problem now is, if you have a multi-party scenario, each party has its own ledger or a log of the events. So what happens is, after some time, there can be problems with diverging logs. So each party records a different kind of thing from the other party. So it leads to diverging ledgers. Then there are also, this can be intentional, like malicious behavior, or it can be purely due to some fault. So let's say one person is actually offline during some moment, so he fails to record some event. So the ledger starts diverging. So the idea of blockchain is, can we collaborate together and create a shared ledger or a shared log which everybody agrees on. So the trust in the ledger comes from these 2 parts. One is the cryptography part of it, which we will see later, and then the distributed validation or the consensus part of it. So as explained in the video, so this is how a blockchain works. So let's say I want to do some transaction, I submit a request. So now in the traditional scenario, it goes to some database where it is recorded, whereas in the blockchain scenario, basically there is a network of nodes or network of peers, what they call as peers. So they basically receive the transaction, and then they validate the transaction based on some predefined rules. So these are called, in the Bitcoin, it's just a scripting language which just says, okay, you can transfer this amount to this person. Whereas in a more complicated scenario, we can come up with what are known as smart contracts, which basically define whether, how to validate a particular transaction, whether this transaction is valid or not. So all the nodes actually validate the transaction, and then once they validate it, they try to accumulate this validated transaction as a block. And then, as explained in the video, again, so basically they try to tie the blocks together in order to get a blockchain. So cryptocurrency is just one application of blockchain. So yeah.
Question. How does a transaction get authenticated? Like, let's say you want to send money to me, right?
Yep.
How does the system of nodes know that you are the real person that actually initiated it, because it could be somebody else that says so?
Yeah, so it basically relies on public and private keys.
Okay.
Yeah, so if the transaction is signed by using a public key, it's basically authenticating you. And the assumption here is only you have your private key.
Karthik, can you repeat the question?
So the question was, how do you authenticate who submits the transaction? Right, so cryptocurrency is just one application of blockchain, so where you're trying to transfer some value from one person to another person. Of course, it has no intrinsic value as such, so if you consider Bitcoin, which is one of the well-known cryptocurrencies, there is no intrinsic value because it is not tied to any of the existing currencies. So it's all kind of traded in the marketplace, and then basically that determines the value of the currency. And it has actually no physical form, and there is no central bank which is kind of standing behind this currency. In fact, most of the central banks are against this kind of cryptocurrency. So what are the key elements of the blockchain? So there are basically 4 parts. So one is the replicated ledger part, which we have already seen. So the goal is have the same ledger at the different parties. So the ledger should have history of all the transactions, and it should have this property of immutability. So nobody, one party cannot just go and change his ledger without consent from the other people in the network. So it's basically append only with immutable past. So those are the key attributes of the ledger part of it. Then there is the cryptography part of it, like for example the identity of the participants, which you raised. So it's basically based on PKI, public key infrastructure, where every person is assumed to have a public key and a private key. So if you sign the transaction using your private key, anybody can verify using your public key that you have signed it, right? And then basically the cryptography also takes care of the integrity of the ledger. So this is the actual chaining part of it, which we will come to in the later stage. And then basically there is a consensus protocol. So this is how do these parties talk to each other and then arrive at the same state. So that's the key part of the consensus protocol. And this consensus protocol, there are many varieties. So it can be completely decentralized. You can do somewhat decentralized and things like that. We'll see all these things in the later slides. And finally, there is this business logic. So this is also sometimes known as smart contract, or in some implementation, this is called some chain code. So this is the functions which define how the chain should work. Like if a particular transaction is submitted, how do you validate it? When should it be added to the ledger? When should it be rejected? And all these things are determined by this business logic. So the logic, as I said, can be from simple coins, as in the Bitcoin case, to what are known as self-enforcing smart contracts, which can be completely kind of legal clauses and things like that. So the main problem here is the Byzantine generals problem, which is a well-known problem in distributed computing for a long time. For example, this paper by Lamport et al. In 1982. So this one is like 30, 40 years of work has been done in this area. So the idea is basically you have multiple generals who want to attack an enemy fort. If all of them coordinate an attack, then they are sure to win. But some of them can be traitors, so they can actually either ignore messages or purposefully introduce miscommunication and sabotage the whole plan. So in this case, how do you come up with a consensus decision when there can be traitors? So that's the key problem which they are trying to solve. So the traitors can be, as I said, they can be purely malicious or could be just faulty or benign kind of thing who just ignore messages and so on. So in the computer science example, the generals are actually computers and messengers are the digital communication systems. And usually this kind of problem is impossible to solve if more than 1/3 of the generals are traitors. Usually you need at least 2/3 of the parties to be honest in order to solve the Byzantine generals problem. So the blockchain consensus is basically a solution to the Byzantine generals problem. So the goal is here maintain a consistent ledger and keep peers or the nodes up to date, fixing errors. So for example, in this case, so these two nodes are working correctly, This one is honest, but it has some problems, so it can be like faulty or miscommunication or loss of messages and so on. So it has in a different state. And this node is actually intentionally malicious, so it's trying to distort the ledger. So the goal is ignore this node and then try to make all the other nodes consistent. Right? So that's a thing which is going on in consensus protocol. So the other part is the smart contract. As I mentioned, this idea was proposed by Nick Szabo in 1997. So basically what he proposed is, can we take, let's say, a legal contract between two parties and then generate a computer algorithm out of it, which will enforce such a contract. Right? So the legal contract is usually some kind of if-then kind of clauses. So if transaction A happens, this is what has to go on, and if that does not happen, what is the other solution, and so on. So can we take this kind of legal language and then convert it into a computer code which autonomously does this thing? And this is very useful in the case of businesses, where the rules are defined by a specific contract, and then when this contract is executed along with the transaction, basically ensure that the transactions are compliant with the rules. And by using cryptography again, by verifiable, signed, and encoded in the programming language. So once it's written into the language, all the transactions are signed by individuals, so you know that you are sure about the authenticity of the transaction itself. Okay, so when you talk about blockchain, there are two possible kind of scenarios. One is known as the public blockchain or permissionless blockchain. So the Bitcoin example which we saw earlier is an example of public blockchain. Then there is also the notion of private or permissioned blockchain. So the key difference between the two is that in the permissionless blockchain, the participant identity is very difficult to control. So you can have anybody writing onto the ledger. So that's the key thing in public blockchain. Whereas in a private or a permission blockchain, there is a little bit of centralization in the sense that there are some rules saying, okay, you do some pre-screening of the participants in the network, and you allow only these pre-screened participants to read or write onto the ledger. Again, you don't trust the participants as such, but then the pre-screen, there is a barrier at the entry barrier, whereas in the public blockchain, there's no entry barrier. So anybody with a computer can just become part of a public blockchain. So the well-known example is Bitcoin, and the other well-known example is Ethereum. So Bitcoin is mainly only for currency, cryptocurrency kind of applications, whereas Ethereum is a more, the smart contracts in Ethereum are more Turing complete, so you can do a lot more things on Ethereum. And the other difference is that in public blockchain, the transactions are viewable to anyone. Since you don't know the identity of the participants, you don't know who is, except for their public key, you don't know who is transacting. So basically the transactions have to be viewable to everyone in order to make a public blockchain work. Whereas in the permission blockchain, so since the network members are known, so you do a pre-screening before adding the people to the network. There is some little bit amount of trust, but you still say that, okay, out of n nodes, only less than 1/3 of the nodes are malicious actually. They are not fully trusted, but then there is little bit of egalitarian trust going on in the permission blockchain. So depending on this, because of this trust differences, the consensus algorithms for public blockchain and private blockchain are very different. So in public blockchain, we have what is known as proof of work or other variants like proof of stake, whereas in a private blockchain, it's mostly Byzantine fault tolerance, which is a key thing. And another advantage of this private blockchain is that you don't have to publish all the transactions to everybody. The ledger is shared, but then some entries in the ledger could be encrypted and can be read only by a subset of participants. So you can have rules like that. So that's where if you want to have some kind of privacy or secrecy of the contents in the ledger, then you need to go for a private blockchain. Okay, So this slide actually summarizes when we should use a blockchain. So let's say you want to reliably store the state of the system. Then if there are multiple people who can update the state, and then even in that scenario, if you can use like an always trusted online third party, then you don't need a blockchain. So only when this trusted third party is not available, so only in applications where you really don't trust anybody else outside the network to do the job on behalf of you, then you really need to go for a blockchain. And the public and private blockchain actually depends on, as I said, identity of the participants. If you know who are the people who can update the ledger, so if the identity of all the writers is known, and if they are not trusted, then you use a private blockchain. So if the identity is known and if you trust everybody to work honestly, then still you don't need a blockchain. So the key thing is lack of trust. And the key differentiation between public and private blockchain is you know the identity of the writers and you don't know the identity of the writers in the case of public blockchain. Right? So this basically gives you an overall view of when you should use a blockchain and whether you should go for a public blockchain or a private blockchain. And this one compares the characteristics. So if you use a public blockchain, the problem is that the throughput is very low. As we can see in the later slides how it works. So the number of transactions which you can execute per unit time is much lower in the case of public blockchain because you need to have a stronger consensus mechanism. In the private blockchain, the throughput is high. Of course, if you use a central database, you can still have much higher throughput compared to any blockchain. So the latency is opposite. So the public blockchain, the throughput is low and the latency is high, whereas the private blockchain latency is somewhat medium and central database, the latency is low. So this other issue which I have already talked about, the number of writers, this is the key. So in a public blockchain, you don't know the identity, so you basically have a large number of writers. Whereas in the case of private blockchain or a private blockchain, you know who can update the state of the system. So the number of writers is low, and the number of untrusted writers is also low. Right? And finally, this centrally managed thing is that in public blockchain, there's no central authority at all. There's nobody defining anything. Whereas in a private blockchain, you have some pre-screening mechanism. So that has to be somewhat centralized. So you need to have some rules on who can get inside the network. And to participate in the network, somebody has to issue you a public and private key pair. Whereas those can be generated automatically in the case of public blockchain. In the case of private blockchain, there's a root certificate authority which will issue you a public and private key. So that's where it becomes a little bit centralized. Okay, so we have seen about the basic blockchain. So the key properties are, we have already seen about the immutability property. So once you add a transaction to the blockchain, you should not be able to change it. You can actually kind of have another transaction which kind of reverts back the state, but the first transaction which updated the state should never go outside the log. So that's the immutability part is one of the key properties of blockchain. And the second is the consistency or the consensus part of it. So all the nodes should have the same consistent ledger. Of course, it's been based on these two properties, we can define other properties like integrity. So you can make sure that your logs are secure, they are tamper-proof. Nobody is going to update, tamper with your logs. And you can actually do a provenance. So if some changes happen, you can actually trace back the whole thing to the first point in time. So that's the provenance part of it. And finally, you have an idea about who updated the ledger when. So it gives you some kind of non-reputability. So these are the key properties or the use cases of blockchain. Okay, so I'll just talk about a few use cases. These are very generic, but then you can also compare or come up with similar use cases in the case of computer vision or AI. For example, let's take the provenance use case. So here the use case is like vehicle maintenance. So the problem here is the vehicle might have large number of parts. It might be a complex system. So you need to know which part came from which supplier and when was it manufactured, which lot, and things like that. So you need to have a database which cuts across multiple parties that keeps a consistent view of all these things. So that's why a blockchain really helps in this provenance use case. So if you take a computer vision system, let's say you're building like an autonomous vehicle with lots of computer vision things, you can have multiple different models coming from different entities, different organizations. And all these people might be updating their models continuously and so on. So you need to keep track of all these components of this AI system or a computer vision system. When was it updated, what update was made, what data it was trained on all these details are required, because once a problem happens, you need to go and trace back where exactly the problem occurred. To do that, all the people who are contributing to this complex AI system should have a consistent view of what's going on. So the other one is a well-known immutability use case. So this is mainly used in financial domain, where once things go inside the ledger, you cannot actually take it out of the ledger. And this is very important for the audit and compliance part of finance industry. And the same can be applied in, let's say, AI. So let's say there are cars communicating with each other, and they send some message, and later they deny that I did not send this message. Then the whole system, the trust part of it collapses. So that's why we need to have this immutability property to make sure that all your transactions, every message which you send is being recorded onto the blockchain. So the third one is the finality use case. So here, again, the idea is you have multiple parties and you have no idea about what the other party is doing. So in this case, let's say a letter of credit. I'm not sure if many people would have heard about the recent bank frauds in India, which are mainly based on letter of credit. So some bank issues some letter of credit to an industry or to some organization, and they take this letter of credit to some other bank in some other country and get money from them. So eventually, the idea is the first bank which issued the letter should pay the bank which actually provided the money. But then there is no way for the second bank to make sure that, oh, this letter was issued by this party and they have agreed to pay the money, because it's just a letter. There's no common system among all these banks which takes care of all this letter of credit. So that's where blockchain comes in. So the blockchain actually, by creating this shared and replicated database, now if you have a letter of credit, you know exactly who issued it and when, so that the other bank cannot deny it. You cannot have fraudulent things coming inside the system.
But you can also, you are also able to solve the problem using private key and public key signing, right?
Yeah.
The bank can sign with its private key and the other bank can verify. You don't need blockchain necessarily.
Yeah, but still you need to have a common database or a shared database among the participants.
And the trust, right?
Yeah, so the key part is the trust. So a lot of things which you can do in blockchain, you actually take the argument and say that, okay, why not have a central database where everybody puts all their transactions, right? So the key part is the trust. So if you don't trust the other parties, and the question becomes like, then who controls that centralized database? So that's where the decentralization and the blockchain is needed. Actually, it's not any magical technology. So a lot of things, if let's say organizations come together and they kind of create trust agreements between them, then probably you don't need a blockchain at all in many cases.
And then can you trust those whatever stakeholders, right?
Yeah. So in the case of financial transactions, let's say you trust your bank to do, say you do an online transaction to transfer money from Alice to Bob, X amount of dollars. You trust the bank to do this thing properly. And then there is a central bank which actually makes sure that all these banks follow these rules. So under these kind of strong trust assumptions, probably you don't need a blockchain.
Also, the we don't realize, but it was mentioned in the video, but we are paying huge amount of premium for the trust, because once I trust the bank has the monopoly over this trust business, and therefore they are going to take as much as, Western Union, if this is the most cited use case, 20% of the money they take as a cut for the trust. So once you decentralize it, then every stakeholder has an equity into the transaction. So you can lower that to 0.1% and things like that. Same thing, Uber was mentioned, and so on and so forth.
Okay, so these are some of the most well-known blockchain implementations. So the blockchain is a very general framework, as we have seen. So there are specific implementations, like what kind of consensus algorithms to use, what kind of smart contracts to use, and then what is the assets we need to transfer. So depending on all these things, people have come up with various types of blockchain implementations. Bitcoin is the most well-known one, which we already see. Then we have Ethereum, which I also briefly talked about. So Ethereum is a more generalized public blockchain, where apart from coins, you can transact many other things. And then Hyperledger is one of the open source ones. And Hyperledger is more of a permissioned blockchain as opposed to Bitcoin and Ethereum, which are more public blockchain. And then there are various other varieties, Stellar, Ripple. So all these banks and technology companies, they come together, come up with various alliances. For example, R3, Cordar, Quorum, Ripple, all these are different financial and technological companies coming together into a consortium and coming up with their own blockchain implementation. Okay, so the next part of the presentation, we will go more deeper into the consensus part of it to understand what really happens in Bitcoin and as well as in other blockchain implementations. So as I said, you can have like 3 different levels of consensus. One is completely decentralized or permissionless consensus, which is the Bitcoin and Ethereum. You can have somewhat decentralized case where you trust some nodes. So then it becomes things like Ripple and Stellar are examples of the second category. And then the third one is a more consortium or the permission blockchain, where the key goal is to have this Byzantine fault-tolerant consensus. Okay, first we will look at Bitcoin to understand more about the consensus part of it. So as mentioned in the videos, Bitcoin was started in 2008 by this person called Satoshi Nakamoto. We don't even know what is the real identity of the person. He just published a white paper kind of thing saying that we can implement such a system. And then a few developers just got in and then they implemented that system. And now it's like market value is more than $100 billion. But we still don't know the identity of the person who published that paper. So it's just a pseudonym. So his goal was, can we come up with an e-currency based on cryptographic proof without the need for any trusted third party or middleman? So that's the key goal. So that this money can be secure and the transactions are effortless. Actually, the problem itself has been talked about since 1980s. There are many papers, things like DigiCash, and so on. Many algorithms which have been proposed in the cryptographic literature to do this kind of thing, right? So actually, this guy Satoshi Nakamoto, he did not invent anything new. He just put together some components which were already available in order to create a viable system, which we will see now. So basically, the key thing which he came up, so there are 3 parts of, to make this e-currency possible, there are 3 things. One is the proof of work mining part of it, which you will see later. So instead of, as mentioned in the video, instead of banks verifying your transaction, now you have a group of miners who are verifying all your transactions. So then the other part is chaining transactions up using cryptography, which is what is known as the Merkle tree and the hash chain. Again, we'll see the details in the next few slides. So this makes the the transactions immutable. But in my opinion, the key contribution of Satoshi Nakamoto, who invented the Bitcoin, is how do you incentivize participation in the network? So why do these miners take the effort to validate all your transactions? So that's where he came up with a clever solution. So what he did is, if the miners actually validate the transaction and create the next block, they will be awarded some X amount of Bitcoins, right? So to do this work, they are actually earning Bitcoins, and then they can use it to cash out at the later phase. So basically, this incentive, giving this incentives for the miners to participate in the network. So that's where the cleverness of Bitcoin comes in. Okay, so we'll see these details in the next slide. So what happens is basically all these nodes, so anybody can actually be a node in the Bitcoin network. So if you just download the Bitcoin software, which is available online, then you become a node in the Bitcoin network, and then you can start submitting transactions, right? So a lot of people submit transactions, and then there is basically a lottery race. So everybody is trying to solve a mathematical puzzle, which we'll see in the next slide. So once a single node actually wins the puzzle, then basically they become the leader and they get to propose the next block. And then this winner's block is executed, and then it gives them the reward is, once a block is executed, the winner of this race is basically awarded some Bitcoins in return. So all the nodes actually, so once the leader proposes a block, then all the nodes can actually go and verify all the transactions in the block and make sure that the leader has not fudged anything. So, and then the longest chain wins.
What is the necessity to have to solve this logic, this hard puzzle? What's the point of that?
So the main thing is you have to okay, we come up to the proof of work consensus here. Okay, then we'll get to that part, right? So what exactly happens is, so let's say I have a bunch of transactions, 0, 1, 2, 3. Okay, so then they basically construct what is known as a Merkle tree. So Merkle tree is a very simple concept. So you take the transaction, you kind of apply a cryptographic hash to the transaction, right? You get 4 hashes. Then you take pairs of these hashes, compute another hash, right? Like that, you keep on building a binary tree until you get to the root hash. So this root hash is, this whole thing is basically called as a Merkle tree, right? So each transaction, right, has a Merkle root, which is basically the root of the summary of all the transactions within that block. So this is a Merkle root. Then it has a hash of the previous block, right? So these two things are fixed. So the puzzle is, can you find a nonce, which is a random number? You can just put some random number in, right? So you basically, can you find a nonce? Then you apply this function, which is basically a hash function. This is a well-known cryptographic SHA-256 hash function. So this hash function takes the Merkle root, the hash of the previous block, and the nonce as inputs, and finds an output. So the goal is to find an output which has a requisite number of leading 0 bits. So this output will be like a 256 bit value. It should have, let's say, 32 bits. First 32 bits of this hash should be 0. Of this output should be 0, or 64 bits of this output should be 0. So you basically change that number, the requisite number, every unit of time. So basically, your goal is to find this random number or a nonce, which will give you an output which has a requisite number of 0 bits. As you might appreciate, so the cryptographic hash functions are one-way functions. So really there is no known solution which can actually give you this number in polynomial time. So the only way is you just keep on trying some random numbers until you kind of luckily pounce upon a number which gives you this output, right? And this number of 0 bits which are required is known as the difficulty level, and the difficulty keeps on adjusting, because as more and more nodes join the network, it becomes easier to find this thing. You have more computational power. So probabilistically, it's very easy to get this kind of thing. So they basically have this kind of every 2016 blocks, they keep updating this number so that the problem becomes harder and harder. Right? Okay, so the question earlier was, why do we need to solve this puzzle? Right? As we have seen, you cannot solve this puzzle using any known algorithms. The only way is brute force. And the brute force is basically computing hash functions. Right? And then basically changing this random number and computing hash functions. And this takes up lots of energy or a lot of computational power. And the idea is, if you are spending so much on your computational power, you are not likely to cheat. That's the basic principle behind this thing.
Well,
right?
As long as I can make more money by cheating.
Yeah, so that's where the real value of how much you can make money by cheating. And then that's why the computational complexity of the problem keeps on increasing.
So I guess that if you didn't have this need to solve the puzzle, I mean, the first node just has to verify that the transaction is valid.
Yeah.
That node can add it to the blockchain and say this makes sense, right? But I guess if that happens, then there won't be any trust.
Yeah. Okay, so we have seen earlier, right, to solve this Byzantine generals problem, the main assumption is usually at least 2/3 of the nodes are honest. But the idea behind major assumption behind Bitcoin is you don't need 2/3 to be honest. As long as the majority of 51% is honest, you can still make sure that the network is working truthfully. So basically, by 51%, we mean 51% of the computing power is controlled by the honest nodes. Right? It's not just the number of nodes which matter. It's the computing power at each node which actually matters. So you can have one node which have large mining farms. They can just create computing centers, put a lot of GPUs, do only this mining. So actually there are specific ASIC chips, like specialized chips doing only the hashing part of it. And you do all these things in parallel. So it's basically measured in terms of the computing power. So like it was mentioned in the video earlier, so right now, to get to this 51%, you need to have more computing power than the 500 most powerful supercomputers in the world today. So that's the amount of power you need to circumvent this kind of thing.
So why is 51%? Why like the majority? Like I can have 30% power and I will also be the majority. The 30% compute power and the others will share the other 70%, but I'm the majority. Why is
No, it's the overall network, right? So if 70% of the network is honest, then the chances of it's basically it's a probabilistic measure of who wins the game, right? So you're trying things randomly. So you might let's say you control 20% of computing power, so you might solve some puzzles, and then you try to play around with it. But then that's where the key thing comes in. So here what is called as the honest nodes don't agree on every block, at least at the current instant. So they agree on all but the last k blocks. So this is the difference. If you're aware of distributed computing, there's basically something called as eventual consistency versus instant confirmation of the transaction. So here the idea is eventual consistency. So right now, if somebody adds a block, it does not mean that immediately the transactions are confirmed, because the last k blocks are still in a state of flux. Like even if you win the game, it does not mean that your problem is solved, because these last k blocks are assumed to be still unstable. And then if somebody else wins the other, so if somebody else wins the next block, and they put the true transactions, and then they kind of build the longest chain, then you lose out, even though you won one particular round of the game. So it's just a game theory kind of thing. Yeah, so coming back to identity, so the idea here in Bitcoin is that there's no true identity required. So anybody who joins a Bitcoin network, they can just generate a public and private key pair, and then their public key becomes their address or the identity. And if you want to transfer money from, if Alice wants to transfer money to Bob, Alice generates a key pair, and Bob also generates a key pair, and Alice just signs the transaction using a private key and sends it to Bob's public key. And everybody else can verify the thing. And basically it's using the SHA-256 hash function and the ECDSA digital signature algorithm. So the thing is, users can generate arbitrarily many key pairs. So as we'll see in the next slide, basically it does not, for every transaction you can just keep on generating new key pair. You don't need to hold the same address for every transaction. Okay, so this is the slide which explains why that is possible, right? So there's two things called account-based ledger and the transaction-based ledger. So in account-based ledger, so let's say you want to execute this sequence of transactions, right? You create 25 coins, transfer to Alice, then Alice transfers 17 coins to Bob, then 8 coins from Bob to Carol, and all these things. Now the new transaction comes in. So Alice says, I want to transfer 15 coins to David. So first you need to find out whether Alice is actually holding 15 coins. And if you do it this way, the only way to find out is try and trace back all the transactions involving Alice to find out what is her current balance in her, or the number of coins in her balance in her account, right? So Bitcoin does not do that. Instead, it follows what is known as the transaction-based ledger. So if you want to do a transaction, you have to provide a previous transaction as input to this current transaction. Okay, so let's go back to this one. So create 25 coins and credit to Alice. So here, this is just a minting of the new coins. So here there is no input, and the output is 25 coins go to Alice, right? Now when Alice wants to transfer 17 coins to Bob, Alice will say that we'll point to this transaction 1 as the input, right? Using this transaction, she will say, okay, here is my transaction 1, which says I hold 25 coins. You take that transaction, pass 17 coins to Bob, and then return the remaining 8 to me. So that's what happens here. So right, so the input is 25 coins, 17 coins go to Bob, and 8 coins come back to Alice, return back to Alice, right? So now to do this thing, let's say Bob wants to transfer 8 coins to Carol, so he will just take this transaction 2 as the input, and then says this one proves that I have 17 coins. So from that 17 coins, you transfer 8 to Carol, and then return the remaining 9 back to me. Right? So if you do it this way, you don't have to go and search your ledger for every transaction. You just look at whether the input transaction is valid and the output participants are valid. So then you can just do the transaction like this. Right? So when here, and this is where the ordering actually, this is where this important concept of ordering the transaction comes in, right? So these 3 transactions are clear. Now, let's say you want to conduct this transaction. Alice wants to transfer 15 coins to David, right? Actually, she does not have 15 coins at this moment. She will have 15 coins only after she receives these 5 coins from Carol, right? So this order is very important. You should not be able to double spend. So the key idea is, so if you have this kind of thing, then you kind of try to preserve the order in the sense that, okay, I have this input transaction. So instead of transferring 15 coins, I just take this. So basically, this input, this transaction actually proves that I have 8 coins. So I can transfer 6 to David and then 2 back to me, right? So then if I can mix and match different input transactions, right? If I can take if this transaction had happened before, then I can take these two input transactions and give it to the network and then generate one output transaction out of it. So basically, in this way, the double spending is prevented. So you cannot have the same, you cannot send the same coins to two different people. The network will detect such an attack. So that's called as a double spending attack. And these are some of the details of a Bitcoin transaction. So as I said, it's basically a script. It says what is the input transaction, what is the output transaction, and who are the public keys of all the participants, right? So it's just a simple script like this. Okay, so what are the key problems with Bitcoin? As I mentioned before, it's using the proof of hashing algorithm for the consensus part of it. The major limitation is that this is highly energy consuming. So right now, to perform transactions in the Bitcoin network, the network is actually estimated to perform this 26 exahashes, which is like 10 to the power of 18 hashes per second. So this is the amount of computational power needed to sustain the network. And it's actually consuming 0.25% of the world energy consumption just to do this thing. And if you want to do a comparison, of course, even if you use a centralized solution or a bank-based solution, let's say like a Visa credit card, you need to have some, because you need to run these servers and all these things. So it consumes energy. But then to transact in a Bitcoin, you need 5,000 times more. It is estimated that you need 5,000 times more energy than doing a credit card transaction. So the energy consumption becomes a major problem. And the other major issue is the latency and the throughput, right? So this is where you need to differentiate between hype and reality. So if you remember the video, he was talking about, you have cars, why do they need to talk to some centralized server which is 100,000 miles away, and it might take forever for this transaction to be confirmed? Can you just do something locally? Can the cars talk to each other? But to do that, you still need to have consensus on what they are talking to each other. And that consensus might take forever. Actually, in a Bitcoin, for a transaction to be to be confirmed, it takes around 60 minutes. So the idea is so the block generation difficulty is adjusted so that on average only one block comes out every 10 minutes. Right? And as I mentioned, so the last few blocks are kind of unstable. So only the last k blocks. So usually the k is assumed to be like 6, so that the probability actually goes down to be some infinitely small number. So it basically takes around 60 minutes for a transaction to be confirmed. So once you submit a transaction and it goes inside the block, you might think that, this transaction has gone through and has been validated. But only after like really 60 minutes, you know that this transaction has definitely been validated and is now part of the network. So due to this reason, the throughput is also very low. So it can process only around 7 transactions per minute. Whereas if you take like a online banking or a credit card kind of thing, it can do hundreds of thousands transactions per second. Okay. Yeah.
So, to me, looking at your last slide, I don't understand anybody who thinks Bitcoin is the future, right? Consuming 0.25% of the world's energy to do 7 transactions a second seems like a rather unsustainable model.
Yeah, it is definitely an unsustainable model. So that's why there's so much of work on what are the alternative consensus mechanisms and how we can get rid or overcome this problem. Yeah, so the next few slides are going to talk about the alternative mechanisms. Right, so Ethereum is another well-known blockchain, public blockchain implementation. It was initially described in late 2013, and then the first stable release came out only in March 2016. So the idea here is, so the Bitcoin is only a script. I showed you this example script for a Bitcoin. You just take some previous transaction and the current transaction, and then just verify some digital signatures. Whereas Ethereum, you have this concept of Ethereum virtual machines. So when you kind of become a node in the Ethereum network, you are kind of installing this virtual machine on your local laptop or your server, right? And then every Ethereum node runs this EVM implementation and executes the same transaction. So here, since it's a virtual machine, essentially you can have more complicated contracts or smart contracts, more complicated logic to define how to validate a transaction, right? And basically here in Ethereum, what they're doing is Ethereum also uses a variant of the proof of work algorithm, but they are also trying different alternative consensus mechanisms such as proof of stake, which we'll talk about later. Okay, so instead of Bitcoin in Ethereum, you have what is known as Ether or gas. So you basically pay the miners some amount of gas when they kind of do this proof of work thing. Okay, so the alternative to proof of work, we all know that proof of work is really unsustainable for anything other than, so that's why if you take Bitcoin, it's mostly used by the underworld today. So there's no real or valuable transactions going through the Bitcoin network. It's mostly used by people who want to really hide their identity. So one of the alternative mechanisms which was proposed is known as the proof of stake. So what do the miners essentially do in the case of Bitcoin? So they are basically kind of committing the computing power or the hashing power to solve the proof of work problem. So basically they are spending something. So instead of doing the computing power, why don't they make a commitment in terms of some currency, right? So that's where stake in currency comes in. So you basically say, okay, I can put in $1,000. So if you find something wrong with this thing, you can take away my $1,000, right? So that's where the proof of stake comes in, right? So you basically stake in currency. You put the currency as the collateral instead of your hashing power, and higher the stake, higher the collateral, right? If you want to do more valuable transactions, or if you basically higher mining power is the same as you putting more collateral into the system. The problem here is, so how do you trust this currency actually? So that's where they actually go back to what is known as peer coin. So they need to have some backup thing called, let's say, like a Bitcoin, through which they can prove that they hold this much currency. So like now, let's say a note comes in, I say I am putting $1,000 as collateral. How do I prove that I have $1,000 with me, right? So that's where again it falls back to some kind of peer coin mechanism. You need to have some other coin like a Bitcoin in order to use as collateral in this proof of stake. So it's kind of getting hybrid. So that you reduce the number of hashing computations. So probably to do this stake thing, you don't need, the number of transactions in the Bitcoin network is reduced. So you can still use the Bitcoin as a base layer, and then use that Bitcoin generated as a stake here, and then you can do the mining for the more complicated part. So in this way, you can do some power consumption savings. Of course, there are other algorithms which are coming in. So one of the more famous one is the Algorand. This is from MIT. Okay, so what is Bitcoin doing? It's basically running some game to randomly select a leader or the block generator, right? So why do we need to have this game to generate this random leader? So what they propose is, they use some concept called verifiable random functions from the crypto domain, and they do what is known as cryptographic sortition. So this random function basically ensures that a random leader is selected for every round, and not only the leader. So the leader is the one who proposes the block, but then you also need other people to approve the block. So instead of sending the transaction to all the parties in the network, you also kind of come up with a committee for every round. So let's say I have a block. Now I want a leader to propose this block and a committee of other network participants to approve the block. right? So they basically use this cryptographic sortation method to randomly generate the leader and randomly come up with the committee. So by using this approach, they were able to achieve more than 100 times increase in the throughput, and then they were able to confirm transactions under a minute. Of course, this is still at the algorithmic level, so we need to have more implementation and more security analysis to make sure that this works. Okay, so these are all for the public. So far we have seen proof of work, proof of stake, and Algorand. All these are for public blockchains where you don't believe anybody in the network. So the middle layer is something called as a somewhat decentralized network. So Ripple and Stellar are two blockchain implementations which use this thing. So here the idea is, okay, I don't trust all the nodes, but I trust a few subset of the nodes, and then this decision can be made by each node individually. So the nodes decide whom to trust. So they basically say, okay, if the transaction is approved by 50 nodes out of these 100 nodes which I select, then I'll basically agree with that transaction. So that's the kind of quorum light protocol. Basically, you can have a heterogeneous validator. So it's again some mechanism of you kind of give up on the trust to improve the efficiency part of it. Right. The third method is the consortium consensus. So here the idea is, okay, the network is limited. As I said, this is for the permission blockchain, where you know the identity of the participants and you know only exactly n number of participants are there in the network. So in this case, my goal is not to get the transaction approved from everybody, but as long as let's say 2/3 of the node approve. So this goes back to the Byzantine generals problem. So as long as 2/3 of the node approve, then I'll just agree with this transaction. So again, how to do this thing more efficiently is part of there are different BFT, Byzantine fault tolerant implementations. Right, so there's so much work which is being going on in the area of blockchain consensus protocols. So they come up with different variations. So there are different blockchain implementations, and within each implementation, they are also trying different consensus algorithms. All these differ in basically their trust assumptions. So some of them require some special nodes, which basically trust. So this is the somewhat decentralized case, and then how many nodes you can, how many malicious nodes you can tolerate. So these are do you need special nodes? What if these special nodes crash or subverted? And then how many nodes you can expect to crash? How many nodes you can expect to be subverted, and so on. So all these algorithms vary based on these 4 factors. So in terms of scalability, so basically if you want to have a public blockchain, you need to have a large number of nodes. So you need to scale along the number of nodes. At the same time, you want to have high transaction throughput. Right? So ideally, we want something here. So far, we are not here. So the Bitcoin and all these things, they can support large number of nodes, the proof of work protocols, but then the transaction throughput is very low. So then you have the standard BFT kind of protocols, the Byzantine fault tolerant protocols. So there, this number of nodes are much smaller, but you can achieve high throughput. So they basically, the other things can be classified somewhere along this axis. So really the goal is to go somewhere here. So once you're here, then blockchain will become a real and usable kind of application, right? Okay, so maybe I just go through the fabric now.
Yeah, sure.
Okay. Okay, so then we have seen about one particular public implementation of blockchain, which is the Bitcoin. So I will talk about the permissioned world also, the private implementation, which is one of the famous ones is the Hyperledger Fabric. So this is basically supported by the Linux Foundation, and it's like an open source, so anybody can actually go and contribute to Hyperledger itself, or I'll explain what are the details between Hyperledger. So Hyperledger is the basic ecosystem which is developed by the Linux Foundation. So this is the basic code. On top of Hyperledger, there are different blockchain frameworks implemented on top of Hyperledger. So it's the same basic code, but then people take it and differentiate it. So that's where all this Hyperledger Indy, Hyperledger Fabric, and so on. So many frameworks around this same Hyperledger thing. And then, so this is still at a level of, this is still at a much lower level. This is just like an OS level kind of thing. So you still, if you want to develop applications, you cannot expect people to go and work with Hyperledger Fabric directly, because it's much more difficult to come up with, like setting up a node, how do you set up the smart contracts, and all these things are much more challenging. So basically people come up with some tools which will simplify this process. So like this Hyperledger Composer is basically a tool to develop something on top of Hyperledger Fabric. So it's basically called Fabric Composer. Right? So in this tool you can probably do some simple JavaScripts to actually run the blockchain network or to deploy the blockchain network. So these are some of the Hyperledger project members. As I mentioned, this is like an open source project. Of course, there are some premium members and general members. IBM is one of the founding members of Hyperledger. Right? So this Hyperledger Fabric is a specific implementation of blockchain technology, and it is mainly designed for enterprise blockchain applications. So it's not meant for, unlike Bitcoin, this is mainly for the permission world. So this is mainly for businesses who want to set up a blockchain among themselves, rather than individuals who want to go and set up a network. Right? And here, basically, the concept is the same. It's a shared ledger, and smart contracts are basically called as chain code in this Hyperledger Fabric. And there is privacy and permissioning. So this is, as I mentioned, you need to have some membership service provider to control who joins the network and to issue them public and private keys. So that's what is called as a membership service provider. And they have the advantage here is that they have a modular architecture, in the sense that if you they don't define the cryptographic algorithms you have to use, or the consensus algorithms you have to use. So it's basically plug and play. So the framework is quite general. So if you want to use a particular type of digital signature method, or if you want to implement a particular type of consensus algorithm, then you can do it easily here. And the current version is version 1. Okay, so I think these details we'll go through in the next few slides. So the idea here is simple. So basically, we know that it's very difficult to make it scalable, to make a blockchain scalable. So basically, what this Fabric does is takes this consensus algorithm and splits them into 3 parts. So one is known as the endorsement, the second one is known as ordering, and then the third one is validation. So this is, you probably can explain with an analogy. So let's say you are working in an organization and you want to claim some reimbursement. So what you do is typically you fill up some form, go and get it signed by your manager, right? So you get it endorsed by your manager, and then you go and give it to some finance department who will actually conduct the transaction, right? So similarly in this case, so this endorsement is basically getting your manager's signature and so on. So let's say Alice wants to do a transaction. She comes up with a proposal, which is just like filling up a form. And then basically for different types of transactions, you can define what kind of endorsement is required. So let's say you're claiming $1 million, then probably you need 4 or 5 signatures along the line. Whereas if you're just claiming $10, you just need your first line manager's signature, something like that. So that's called the endorsement logic. So you, based on this proposal or the transaction, you go to these endorsing peers. So everything here takes place automatically, right? So nothing is manual. So you just go to these endorsing peers who will check your proposal and say that, okay, this conforms to all the rules. And then they will sign the transaction, which is called as the endorsement. Right? So once all these transactions are endorsed, you give it to the ordering service. So this ordering service will basically say, okay, how do I create these blocks? So it will take these endorsed transactions, put together as put them together as blocks, and then send it to these committing peers who will actually commit it to the ledger, or who will actually write it to the ledger. So there are three entities here. Of course, the same peer can act as an endorsing peer, as well as a committing peer and ordering peer, right? But then the roles are slightly different. So that's the functionalities are separated out. So you have endorsement peers, you have who basically sign the transaction, and then this ordering services which orders a transaction, puts them in the block, and then the committing peers who actually write it to the ledger. And before they write it to the ledger, they actually do another level of validation, which is basically see that, okay, does this transaction really conform to the rules, and does it have the required number of signatures from the endorsing parties. Yeah, so this explains how the transaction endorsement is done. So basically you send, so in this case of blockchain, is a transaction proposal is just a read-write set. So you read something from the database and you want to update the database. So you want to write something back to it, right? So let's say I read these fields, some specific fields from the database, and modify their values and create a write set. And basically this endorsing peers will actually first simulate the transaction. They will look at what their current ledger and then say, okay, whether this read set is valid and whether the write set is valid, and whether it conforms to all the smart contract rules. So if it conforms to all the rules, then they will just sign the transaction, digitally sign the transaction, and send it back to the proposer. And then the proposer will actually send it to the orderer. And to do this, as I said, everything is based on predefined rules, which are known as smart contracts or chain code in the case of Hyperledger Fabric. So they have this endorsement chain code ESCC, and the validation system chain code, which is actually the final validation of whether the endorsement has been done. So all these chain codes, they will check whether is the endorsement valid, are there appropriate number of endorsements, are the endorsements from the expected sources. All these rules are basically defined, and you go and check before you commit the transaction to the ledger. And in terms of consensus, as I said, Hyperledger Fabric is modular, so you can have different types of consensus algorithms plugging into it. You can have like a simple solo order. This is a centralized kind of solution. Usually this is used for some testing cases, not for practical implementations. But typically for a practical implementation, we go for something like a practical Byzantine fault-tolerant algorithm. So this is a well-known distributed computing algorithm, which the problem is it requires more communication between the nodes and so on. So it's less efficient. And this fabric also introduces this concept of what is known as channels. So you can understand channels like sub-blockchains out of the main blockchain. So let's say I am part of a blockchain network. My bank is also part of a blockchain network. So and I'm transacting money to somebody else. So basically only myself, the other counterparty, the counterparty's bank, and my bank. Only these four entities need to know about the transaction. All the other entities, they don't care what is happening, right? So they just sign the transaction and go away. So that's why Fabric introduces this concept of channels. The way channels, you basically, there is one big blockchain, but then different entities can access only some parts of the blockchain or some kind of transactions in the blockchain. And that concept is defined. So which part is accessed by which entity, so that's called as a channel part of it. And of course, as I said, there should be a membership service provider who kind of determines who should enter inside the network and how their keys should be distributed and so on. So this slide actually shows a full transaction lifecycle. So as I mentioned, you have an application which basically generates the transaction. You send it to the endorsing peer. You get the endorsement back. So you submit it to the orderer who puts it into a block, send it to the committing peer who writes it to the database. Okay, I think we can go for a break now, and then come back and look at this sample implementation.
Any questions?
Any questions so far?
Are you able to make these slides available online? After the tutorial?
Yeah, we can put it online. We can put a PDF version of it online. So if there are no questions, then we can just go for a break and come back in 10 minutes. Okay, thank you.
Maybe play the remaining part of the YouTube.
The video.
Yeah. Because a lot of people were not there.
Maybe I just play from the beginning.
Yeah. People were just.
Hi. Yeah.
Today, my talk is going to be about decentralized artificial intelligence, aka what happens when we take the two hottest technologies of today, AI and blockchain, and put them together, right? Just sprinkle everything on top of each other, right? So let's get right on into this. We've got a lot to cover. So, machine learning, AI, this has been around since the 50s. It's not a new technology. It's a pretty old technology. But basically, the idea has always been the same. We have some data set, right? Some input data set. And we have some objective. We have something that we want the AI to do. In this case, classify a car. Is it a car or is it not a car? So what we do is we feed this AI a bunch of images of cars. So think of it like an Excel spreadsheet with two columns. In column 1, you just have pictures of cars. In column 2, you just have labels. Car, right? And so the idea is that the AI learns the mapping, the relationship between the input data and the output labels. There is some relationship between everything. There is a function in life for everything. But that's a bit of a tangent. The idea, though, is that the human would have to extract all the features of what it means to be a car, right? This is kind of what a car looks like. This is the shape of a car. This is what the exhaust pipe looks like. And this was a very tiring process. But this is what humans had to do. We'd extract features by hand. And so what happened is, once we'd extracted those features, we would feed it to some kind of machine learning model, and there's a lot out there. Eventually, it would learn the mapping, and then give it a new car picture, and it would know, hey, this is a car. But a few years ago, there was a scientist who said, let me take one specific machine learning model called a neural network, enter, drop the beat, right, drop the mic, and feed it lots of data, and lots of computing power, and add a lot of layers, deep layers, aka deep learning. That's what we call it. What happened is, when we did this, it started outperforming every other machine learning model. And now, deep learning is the hottest topic in machine learning. It is outperforming everything else. Self-driving cars, drug discovery, everything hot that you're hearing about AI is coming from deep learning, okay? So that was my one-slide overview of AI. So now, blockchain, right? So a couple years ago, there was a programmer who no one knows, named Satoshi Nakamoto, who released a paper on a cryptography mailing list detailing a system called Bitcoin that allows two people to transmit value online without needing a third party, namely a bank. So what happens is, instead of a bank being the third party, there are a group of people called miners. And anybody can become a miner. You just need a laptop, right? Anybody can become a miner. And the idea is that when I transmit value to you from me, these miners have to approve this transaction. They have to say, okay, let me check this list of transactions. So every miner has a copy of every transaction that has occurred in the network. And they have to approve whether or not this transaction is valid or not, right? Because they have the list. So you might be thinking, wait a second, couldn't someone just create a bunch of accounts and say, hey, I'm the majority of the miners, because the majority of the miners have to approve a transaction for it to be added to this list of transactions? Well, no, because Satoshi said every single miner has to prove that they have solved some random mathematical problem. It's called the proof of work algorithm. And that means that you have to have more computing power than the 500 fastest supercomputers in the world combined to have the majority of the computing power in the Bitcoin network. And because no one has that much computing power, no one's been able to hack Bitcoin. And that's why it has a over 100 billion market cap as of yesterday, more than the GDP of some countries, and no one's been able to hack it. It's been around for a decade. It's a really powerful technology. Let's keep going here. But the really, really interesting part about Bitcoin is not the actual application, but the underlying data structure of Bitcoin. So this is kind of a rough diagram of what it looks like, very simplified. But the idea is that we have some list of transactions, right? I'm talking about this list of transactions that all of the miners are holding. And we group these transactions together into little groups that we call blocks. And each block points to the next block. So one block is like, okay, I'm a list of transactions, here's the next block. And the next block's like, oh, thanks for that. Okay, here's the list on the next block, right? And it becomes this kind of chain of blocks, aka blockchain, right? So it's a blockchain. That's what we call this data structure. And because of the proof of work algorithm, no one can modify it. It's an unalterable, immutable in computer science terms. Shout out to all the programmers out there. It's an immutable data structure that no one owns. And this is a very powerful idea. So I like to call this the yin and the yang of AI and blockchain, right? These two technologies go really well together, but no one's really put them together yet. So this is a very futuristic thing. So the yin is AI. AI is probabilistic. It's all about computing the likelihood that something will happen, the prediction of the future, using what it's learned. And an AI is always changing. It's updating its weights. It's learning about the future. And an AI is a set of algorithms that guess at reality. The yang part are blockchains. Blockchains are not probabilistic. They are deterministic. You know exactly what's going to happen, right? They are permanent. They are unchangeable. And they are algorithms and cryptography to record reality. So these two things can go really well together if you break them down into what they're really good at. So we live in a world where we are all using these services, right? And these services collect and monetize our data. That's the business model. But this is a problem because our data is the most valuable thing we have, and it will become more valuable as everything is slowly automated. Your data will be the only agency that you have. It will be your most valuable asset. So you need to own it. But right now, we're giving it away for free in return for a free service. Ideally, these services would be paying us for our data, right? But that's just not the case right now. We need to redo all of these apps that we have in Web 2.0, everything from eBay to Uber to Lyft, all of it, Facebook, right? Morally speaking, this is a terrible idea to let some humans control our data. In the case of Facebook, they modified the newsfeed to affect large swaths of the populace. And the 2016 political elections, for example, in the US, it's just very corrupt. It's just not a good system. And not even talking about it morally speaking, let's talk about it technically speaking. Centralized systems are not good. Take the case of a self-driving car network. Let's say we've got 3 self-driving cars at an intersection, okay? 3 of them at an intersection. And they're trying to decide who has the right of way. But if there was one central server that they all had to talk to 1,000,000 miles or kilometers away, then it would take forever, and there would probably be an accident. Ideally, these cars could talk to each other without needing a third party or a central service or a server. So both technically speaking and morally speaking, creating what are called decentralized applications is a really good idea, and it's what we call as developers Web 3.0, and that's what's happening now. If you're looking for something to disrupt, you take blockchain, you take AI, you combine them together, and you create apps that have never before been possible, and that's the most exciting thing these days. So this leads us to this idea. It's a very abstract idea, but it's starting to happen, of what are called decentralized autonomous organizations, or DAOs for short. You can also call them dApps, decentralized apps. But the idea is that these are apps that are run and maintained by the community that uses them, right? So think of Uber, for example. When I'm a rider and I'm trying to find a driver, I have to use a third party, namely Uber, to find that driver. And so Uber takes a cut of this, and they have a bunch of malpractice as well that we all know of through all of their scandals. But ideally, I wouldn't have to trust Uber. I could just find my driver. He would get paid more. I would have to pay less because there's no third party. So it would be better for both of us, right? We would all earn some equity because we are all a part of the network. It's not just about earning money. We'd also earn equity, and we would be able to decide on the features of the app. So it would be a more democratic process, right? It's kind of like a community-owned grocery store, for example. Instead of one central person owning it, everybody who is a part of the network would also be a participant in the infrastructure of that network as well. So there's a lot of good that can come from this. And that's what we're going to start to see as we move towards Web 3.0. If you're looking for a really hot idea, something really cool to do, this is it. Blockchain, AI, combine them together, use this immutable ledger, and have an AI live on the blockchain, or at least speak to the blockchain, and data is being pointed to some distributed hash table or some kind of decentralized storage source. And then there's a whole token model. I've only got 2.5 minutes, so I can't explain everything here. But there's so much. There's so much. That's what I'm trying to say. But it's not all good. There's also bad. I can't talk about the good without talking about the bad, right? So imagine this. What you're seeing here is a picture of art that was completely generated by AI. There is no human in the loop. So imagine an AI that lives on a blockchain, and its job is to just generate art. So what it does, it does this. It generates some art. It then sells it on some marketplace. It earns some money. It uses that money to feed itself more computing power. It uses that computing power to then generate more art. It just keeps amassing wealth. And no one can shut it down because it lives on a blockchain, right? No one can shut it down. You'd have to have more computing power than the 500 fastest supercomputers in the world combined to shut it down. Eventually, it becomes the wealthiest entity on the planet, right? So that's kind of scary if you think about it. It's an unkillable AI, and it lives on a blockchain. So how do we stop this? Well, it's our responsibility as developers, as people who don't even program, to educate ourselves on how this intelligence works. And only then will we be able to stop any kind of malpractice, any kind of bad scenario, right? The will of the collective will override any one bad actor. So we have to educate ourselves, be more aware. One resource for this is my YouTube channel, but the internet is your university.
So welcome back, everyone. Before we move into the applications in the computer vision domain, I just want to show you some sample blockchain implementation. So I'm just taking a simple Hyperledger implementation. So there is a website from IBM which provides some sample code. So okay, so this is the website. The link is mentioned in the slide. So if you go here, there are basically a few simple starting implementation. So if you want to learn about blockchain and how to implement it, you can go here. Okay, I'll just show you. There are many simple examples, so I'll just show you one example, which is so decentralized energy thing, right? So here the idea is, let's say you are generating some renewable energy at your home and you want to sell it back to your utility company and the grid, right? So you have residents generating electricity, they want to sell it to the utility company, and then the utility company gives back. They don't give you cash, instead they give you some kind of tokens or coins which you can go to a bank and encash. So there are basically three parties here: the resident, the utility company, and the bank, right? So actually there is a this one, you can click this link or get the code. You go to this GitHub repository, which basically says how you have to what are the things you need to install, right? And how do you kind of set up the system, how do you run the smart contracts or define the logic and all those things, and then how do you create participants, and finally how do you execute the transaction. So all this is listed in this GitHub link, right? Like I said, there are basically, so for this example there are three participants: residents, banks, and utility companies. And so you can have different kind of transactions. So let's say the resident can sell to the utility company, so that's energy transaction, and then in return you get coins. And then the resident to the bank is you send coins and get back cash, or you give cash and get back coins. So these are the kind of transactions possible. So this is actually using Hyperledger Fabric, and it specifically uses Fabric Composer, so things are much simpler if you want to set up the network and so on. So if you go to this models page, okay, so basically this is the model.cto file. So this is how you can define, let's say, participants in the blockchain network. So you have one participant is a resident, one participant is a bank, third participant is a utility. Then you can define what are the attributes of the participants. For example, you have a resident ID, name, and so on for the resident. For bank, you have a bank ID and a bank name. Utility company, again the ID and the name. And then what kind of assets they can handle. So for example, the resident can handle coins, cash, and energy. Bank can do only coins and cash. Utility company can do only coins and energy. So you can basically define different assets, who will own these assets, who will transfer these assets. So all these things can be defined using this kind of file. Yeah, so this is the test data. So this basically defines all the functions, like who can access. This is actually the chain code or the smart contract part of it. So you can write everything in like simple JavaScripts, and then immediately start running the blockchain network. So if you follow all these instructions, setting up of the the Hyperledger fabric, the fabric composer, and then deploying all these networks is all mentioned in this GitHub link. So if you want to try some simple blockchain applications, you can try this kind of thing. Okay, so are there any further questions about blockchain before we move into the applications part of it? Okay, I'll hand over to Sharath to take you through the applications.
Hello. So we started the introduction by saying that the AI is for predicting what is going to happen, and then blockchain is for recording it. So what all can be recorded can be nicely grouped into 4 categories. There are other ways of categorizing possible, but we found this very useful. People, objects, of course, people are also objects, but thinking of people as, one of the mainstream category. And then objects, models is just like, what in the machine learning models, how we are going to model people and objects or other things recursively. That is the models themselves. And the data which is sensed from people and objects would be a content. So those are the 4 main categories we think in which we can do these blockchain applications and various features. So what I'm going to do is that take one by one and see. Again, this is just a very emerging, like you saw in the video, very emerging area. Not many applications are there, but this is really where the opportunity is for all of us to make an impact in terms of the marriage of computer vision and blockchain. So the general structure in which I am presenting this is that there are not many real systems. Instead of that, what I'm going to show you is what is the problem space looking like, what are the requirements and challenges. And we have done a little bit of a work here, so 1 or 2 papers we'll review it, but this will be a good place where we can brainstorm. So starting with identity management, the broad way you can think of this as that, who are the people, including their digital counterparts, how are they being recorded today? And most of the time it is some central authority who is, right, let's say you are working for a school or a company, then some central IT database is modeling your login ID, what is your access rights, what are your authentications, etc. And like Karthik said, if you really totally trust that person or the entity or organization, there is no need for blockchain. But if you don't, or there are better, more novel ways of managing that identity in a distributed way without trusting a central authority, then there is a lot of applications around that. I'll review some of the applications that are currently there in terms of blockchain and identity management. All of them are related to the encryption, around encryption technology. Nothing related to the person as you are. It doesn't link the person and the identity. So that's where the main opportunity for innovation is. So I'll first review what is there, and then we'll look for the gaps and one or two applications which are just emerging, and our own work, little bit of work we have done around how to connect the physical identity of a person and their representation. We'll show you just one method, couple of methods, and then we can take some question and answers around the identity. And we'll do the same thing for the other three categories. So again, this is a recap. Identity is stored in centralized servers. It is not only vulnerable, but very expensive, as there are breaches, as you can see in many, many news items, that the identity, credit cards related to people, etc., are hacked, and then there is a huge amount of damages done. Can it be done in a distributed and transparent fashion, which is going to benefit all the three stakeholders? The consumers, because I know out there what is all. Today I don't know what my IT is holding as a representation of me, whether it is true or not true, and so on and so forth. It's not transparent. So if it is going to be distributed and transparent, it is going to be advantageous to me. For the businesses, because it is the reduced risk, because once it is distributed, there is a lot more due diligence around it, both from their own point of view, but also there are a lot of regulations around it, especially when it is related to, financial accountability and so on and so forth. So all stakeholders are benefited by having a more distributed, transparent, and immutable records of it. So there are, already dozens of companies who are doing digital ID management using blockchains, and we'll review them very, very quickly, and then see that what are the remaining gaps in terms of what is not done and what is the opportunity for innovation. So see, the secure key, again, all of them, very summary way of telling this is that the digital identity is related to some kind of a cryptographic key, and the cryptographic key solely represents your identity, and that can be documented on a blockchain as opposed to on a central server. So we are not going to review anything about the central server, but the new ideas that are coming from all these companies that I flashed in the previous slide, they all basic idea is that somehow you take the identity cryptographic key associated with the identity document, reader document, etc., and put it that in a form inside the blockchain, so that you will have the transparency and distributed nature. So this particular secure key, what it is doing is that it is using, first of all, IBM's blockchain for Hyperledger for doing the identity management. And then, the credentials, the secure credential networks between financial institutions, right? How, you have two accounts with Bank of America and then, Bank of London, then how do they talk to each other using, something that, a sharing network between these two institutions, so that you are the same person across these two organizations. Other one is, it extends the entity beyond just the identity. It could be not only identity, but an application or a device or an organization, or it could be even just a abstract quantity like a bot. You can create, a smart contract related to these identities and put that on the chain, and then use that for, automatically doing the blockchain related smart contract executions. This one is very interesting. The blockchain, basically you have a lot of documents related to the person, right? A birth certificate or a marriage certificate or a deed, and you want to create these contracts related to particular documents and related identities by chaining them together and that aspect is particularly capitalized by BitNation. Again, similar idea here is that, how do you make the claims related to the identities interoperable across the silos? That's the basic concept in this hyperledger, indeed. Again, just one specific patent we'll talk about where this comes from the breeder document terminology, comes from biometric world. How do you know, a lot of fraud related to identity of a person is related to breeder document. Breeder document means a document which proves who you are. And, one example of that is a birth certificate. Many times people who want to create fraudulent passports or something like that, what they will do is that they will take a deceased person's birth certificate and somehow link a completely different person with that person because they know that that person is no longer there to claim their identity. So this is how the fraud happens. Now, so far what we have seen here is that the document, person, all of these are related with respect to the person in terms of an encryption key. It is not really relating that person and the encryption key. And the idea is that biometrics, which is part of the computer vision, where you are using face, fingerprints, iris, and all these other physiological, behavioral traits that are related with respect to me, can they be linked to this kind of breeder document? And this patent which really capitalizes this is that as soon as somebody is born, you trust, let's say 3 authorities: parents of the infant that is immediately born, a government official, and a physician who was assisting the birth of the infant. All of these 3 are kind of the stakeholders in that consensus algorithm. And as soon as the person is born, then you take whatever biometrics that are coming out of the child, link it with respect to timestamp and all these other birth certificate related, the weight of the person, weight of the infant, and the length of the infant. All of the auxiliary data that is there today in the birth certificate. Along with that, you take the birth certificate, and these 3 stakeholders agree and create a block on the blockchain. So, as the children, grandchildren, others are born, these blocks are all related, and that creates a pretty good proof of this particular birth certificate is yours and not somebody else's. Because if somebody else wants to really verify, is this your birth certificate, they can go through, biometric verification process to say, this is indeed yours, and nobody can forge a deceased person's birth certificate for yours because of the use of the biometric in the blockchain process. Does that make any sense? Any questions related to this? So right now, like Karthik said many times, the identity in a blockchain world as it exists today is just a cryptographic key. You need to link that to a actual persona, and biometric is a way to do it. So we recently wrote a paper on the how, typically, let's take the example of how do you board a plane, right? Today, you typically show a boarding pass. To get a boarding pass, you need to show your driver's license to somebody. Somebody sitting there who's actually looks at you briefly and then looks at the photograph on either passport or the driving license, and then says, yeah, this is the same person, and then they issue the boarding pass. But what is the counterpart of that in terms of completely electronic process. So in a centralized system, what one could do is that, simply there is think of a system which is doing face recognition, for example. Um, you show your driver's license or the, uh, your authentic record of comes from DMV, which is the in US organization which maintains, the record and photographs related to you with respect to your driving credentials, which are also being utilized today as first class um, identity record, formal record, right? So one could think of a centralized system where you show up at an airport, you claim that you are, Karthik Nandakumar or Sharathchandra, and then it pulls up the record, matches it, and says, yes, this is the same person, and then issues a boarding pass. What this particular work that we are trying to solve is that how can you do the same thing on a blockchain, and what additional features one could get by doing it by blockchain. That's the application that we are trying to build. And the basic process here is that, once the boarding pass is issued in a centralized system, right today, in fact, once you get the boarding pass, somebody steals your boarding pass somehow, there is no way we can stop them, right? They can board a plane, do whatever, because once the boarding pass is issued, it's all, from there onwards, there is no more check. In a blockchain-like system, what one could do is that, you could have, easy revocation system. You can say that, you come back and say that I somehow misplaced my boarding pass. Can you revoke it? Can you put a deadline saying that in 2 hours it is not is used, then automatically it is null and void. Can you come back and reissue it? All these kind of features one could add, because once you have put up the record of this boarding pass in a blockchain, two different authorities. One, the issuer, who is giving at the reception where the ticketing is done, and the redeemer. Redeemer means the person who's at the gate. They are two distinct physical authorities, and these two authorities can separately keep tab of these two, whether boarding pass has been issued, whether you are eligible, whether you paid, and all that, the issuer's concern. Whereas the redeemer's concern is that whether all of these, whether the boarding pass is still valid, it is stolen, somebody is reclaiming it, and so on and so forth, is the redeemer's concern. So those are two separate authorities. Because of the blockchain and distributed nature, you can enable many of these additional functionalities by introducing this distributed ledger system. And this is just one implementation, but this is being presented here as a example only. You can think of, as some of you may be already working in face recognition and others, you can think of many more applications, more interesting applications around this, but this is just one application we are going to talk about. Right, I talked about this, most of it, how the airport as this one process, but it is, even though the airport is just one use case, but similar things happen, sporting tickets and things like that, where you buy a ticket and then there is a lot of abuse going on related to, if I'm a illegal seller, I'll buy a lot of tickets beforehand cheaply and then later on sell it to somebody. How can I prevent that and things like that? So many times when somebody's selling a particular access, they're thinking that somebody's end user. They don't want to sell it to somebody, quote unquote, middleman, if their intent is not legitimate. So lot of these processes have similar kind of application as the boarding pass. But again, we'll leave it to your imagination where all these kinds of problems appear. But again, lot of room for innovation where recognition, where computer vision community has mostly talked about central. They assume that, once I match a fingerprint or a face with a database record, the application is no longer interesting to me. That's no longer the case. There are many, many new features one could introduce based on many application requirements once you have a distributed ledger. So two brief scenarios we talk about in here is that one, like I said, where the boarding pass is out there on the infrastructure. That means it is sitting there on the airport network. Whereas the other one is that you give that boarding pass just like the today's boarding pass, but it is in somebody's smartphone. If you are the user, then you can give it to the user. So those are the two different scenarios. They both have some plus or minus. We'll in the slide deck that we are going to share with you, we'll also put the link to the detailed paper, but here I'm going to just summarize it. So the basic idea is that, again, what you're going to begin with is that a user comes in and they, at the beginning, they will say, here is my fingerprint, and whatever the current process is that, right, you have to have an electronic ticket number, whatever, they will input it, and out comes the token, right? Out comes a biometric token comes back to the user. And there is a huge blockchain network, which we'll describe in a little bit detail in the next couple of slides. But in the end, what will happen is that at the gating, which we call as the redeeming process, once they give the token, then they can get into the plane. And in between, we'll show you what all things happen and how it is different from the two things. So two things of importance are that issuer and verifier are two completely different authorities, physically separated, and then what all has to happen to make this all work together. So the first process, what happens is that the user gives the biometric enrollment process where they are giving their face, fingerprint, whatever it is, and you do feature extraction. And then those of you who are really familiar with the biometric literature, sometimes you don't want your fingerprint face out there. You want to, somehow protect it by either transforming it, which is called as anonymous biometric, or creating some kind of a surrogate representation which corresponds to your face, but it doesn't disclose any sensitive information. So you can do all of that processing here so that if somebody steals it or gets into access, then they still don't know how your face looks like, etc. So that's an optional process. After that, what you do is that you create a pseudo-random key, and you generate an encryption key out of it. And at the same time, you're also creating, again, all of the details are there in the paper, but basically there is a two-phase process. One is you're generating a representation of your biometric token given back, let's say, to the user through a cell phone. It gets stored in the user's cell phone. And then through a process called as, sharing the key, you use that key, split into whatever number of, you remember in the blockchain there are multiple peers. You split that key into multiple shared secrets. So so on one hand, the user gets a part of the token which represents not only the authority but also their it also gets embedded the biometric token, and then this key gets split into multiple shares, and each part is worth only 1/n of the agreement that you can get. So again, this I described already that once the key gets split into multiple keys, and each one of the peer gets one key, one part of the key. At the redemption process, what happens is that once user puts in the key, so first the interesting part is that each of the peers has only part of the, think of this as a, you can't make the whole dollar because the dollar is split up into whatever number of parts. So unless they all are joined back together, it's not the worth of $1 value. You can't take just one small piece and say, give me 20 cents, unless the whole dollar is stitched back together. So that's what is being done here, is that you're taking all these, each of the peer, if they agree, they are worth only 1/n of the consensus. All of them are agreeing, or a majority of them agree, then you can recover the main key, and that key along with the user's key taken together you can have your the authority to go to the gate or go into the plane. So the basic idea is that the key gets split into multiple portions, and unless there are majority of these agreeing that this is valid, you will not be able to authorize the user. So again, people who are interested, I don't want to go into the details here in lot more details, but various revocation scenarios, etc., can be handled. If you cancel the purchase, you can go back and show the token and say I don't want to go on the plane and get back the money. Or if you suspect that somebody else got hold of it, you can go back to the gating, the reception, and get back your money's value, or reticket it, cancel the first ticket because the first token, because you already know that token is not going to be utilized. So you can go back to the blockchain and change that to saying that it's no longer valid, and so on and so forth. So again, I won't go too many details, but I think the main purpose of this use case to show that going from centralized to the decentralized, you can add more features, and then from the blockchain point of view, even though there are dozens of companies who are doing identity management, today there is not very credible application out there which is using biometrics as a way to tie together identity and the digital record. Again, going the same theme a little bit further, that today, the blockchain identity is almost primarily related to the cryptographic key. So if you have the cryptographic key, no questions asked, that you are the uncontested owner of whatever assets that key has access to. And that has led to many of the problems, like stolen, if somebody lost their key somehow, or hacked into, they put it in a key, electronic key, and somebody stole it, got access to it, it's all gone. And again, we don't have a quote unquote solution, but I think this is where a lot of you who have biometric experience can build an application where how you can introduce identity that is more than cryptographic key, which can be easily misplaced or stolen, and so on and so forth. So that's the idea for that. So again, Yeah, the same idea here a little bit, that how do you tie that to, cryptographic key with what you are, which is basically the biometrics, because right now most people have tied it to what you know or what you have, but not to what you are. And this is where one of the major computer vision applications for blockchain will emerge, is our hope. The other application we thought about again is that, unlike you're trying to log in into a server, right? And somebody's trying your username and the password. That is a little bit different than on the blockchain, because in blockchain, of course, in real server also, you can say, from which IP address you're trying to get access and so on and so forth. But in a blockchain system, you can build much more elaborate infrastructure to see where somebody is trying to get access to what kind of key. And the basic idea is that you can create systems and applications where you can create irrefutable records of who is trying to log in where are the unsuccessful logins are coming, and you can mine them to not only detect but also deter, because once attacker knows that all of this is being logged, then they will be deterred not to attack the system. So that is another theme of application where one could try to innovate. Again, some more ideas here in the spirit of brainstorming, that really most of the identity systems today are not really looking for you. How do you look, how long your nose is, or how your eyes look, or what color of eyes. They just want to know, some kind of a proof of residency, proof of age, and things like that. And many times these can be used as surrogates for the identities, and can be gotten out of your physical activities through computer vision. That's the basic idea. So I'm going to transition into the next part of the artifacts. Remember the 4 quadrants: identities, objects, and the content is what you sensed from the either objects or the identities through the sensors, and then inference is the 4th quadrant. So we are going to go into the content. Broadly, the content today, as on the blockchain, is authenticated by, I'll show you some examples. What you do is that you create a cryptographic key or a hash, put that on a blockchain. That's the extent to which the blockchain guys have innovated with respect to content management. But there is a lot more new requirements are coming in terms of what can be done for the content management. Just as we were talking, somebody came to us and said that they wanted to authenticate their content in management in a little better way. So if you think about it, as you go into the real world, you will see lot more new requirements about how the content needs to be managed than the traditional way. And the already existing patents today, most of the ideas that they are talking about is that, oh, you take a content, it's a picture, it's a video, you create a big hash key, put it in the blockchain. That's the extent to which the state of the art is there. But what we are trying to say is that there is more than that in terms of requirement. One requirement will flesh it out a little more in detail because we have studied it, but you can come up with your own flavor of it and innovate. There is a lot of opportunity to innovate in that space. So first I'll go through the existing literature a little bit. Most of it is in terms of patents, and then we'll talk about one paper we have written recently around this idea. And then maybe again we can have some question and answers. And feel free to, this is mostly, as you can see, not much work is done in terms of computer vision multimedia, and so on and so forth. A lot of work that has been done is very, very traditional and almost obvious. But again, a lot of opportunity for you guys, for all of us to innovate. Any questions so far? So again, in terms of content management, as you know, right, at least people in the US know that, how the content is being manipulated with increasing amount of, sophisticated processing to generate fake data, fake news. And like in the video YouTube that we shown, the US lost, according to some, even the last US presidential, elections have been tampered because of this influence of fake news and other kinds of stuff. So on one level it looks like something that only researchers are interested in, but on other level it has a real serious consequence in terms of the way we live and the way we respect our values in terms of democracy and so on and so forth. So the 4 things that we are talked about grouped into 2 is that if this is a particular piece that I'm going to see on the Facebook or wherever on internet, how do I know, is it where it came from, or somebody else tampered it and put it in here? So just one comical but real example is that after then President Bush was talking to a little kid, somebody tampered. You can't see it here, but here you can see the America is spelled upright, but now the America is here. So it's exactly same picture, but now tampered with the book upside down, and it's so very real. Looks real, but it is tampered, and it's basically suggesting that what President Bush is talking, he doesn't know what he's talking about or something like that. But this is just one innocent example, but there are many other examples which could sway the population's opinions and have major consequences. So the 2 problems that one is interested in is in provenance, basically, which means what is the source of the data, whether it is came from where it is claiming to be coming from or not. And the other one is that after they did it, somebody tampered it or not tampered it. And those 2 are the main, and this is where a lot of our computer vision related, multimedia related analytics and other expertise can be used. And again, I'm going to review some of the literature here, but most of the literature is that you take a picture, like if that was a picture, you take that picture, put the hash of that picture on a blockchain to say that is a true picture. But as you know, even a small change, right, 1 pixel change, the hash of that is going to change a lot. It's not going to really remain the same. So the expectations that it is going to be the exact copy is not very realistic in our opinion, right? It could be downsample, upsample, and still you should be able to tell the integrity of this particular image and so on and so forth. It doesn't live up to that expectation. And so without much further details, I'm going to show you that. Again, another big application around this is that not just the content on the internet, but lot of, at least in the US, there is huge amount of money being spent on body cams, because there are a lot of accusations that police used a lot of brutality when it was not needed, and other way around, some very controversial victims, they will come and say this particular police officer used unnecessary force, although that is may not be true accusation. So both ways, the body cam related, the police officers are these days having a body cam on them. And again, police officers is just one example, but very sensitive example. But lot of professionals are these days in their workflow, they are using body cams not only for defensive purposes, but for also to improve their workflows, make collaboration better, and so on and so forth. And whether the content that is coming from that, is it authentic or not authentic, is the other part of the story. So, like I said, the patents and initial literature that you see today is that most of the time, this particular one video integrity example coming out of I think one publication, but also there is a patent around it, is that when two cars collide, there is a as soon as you detect collision, you are taking a piece of video coming out of the camera and putting the hash of that on a blockchain. That's the basic idea. And then you can also add other auxiliary data related to where the location was and so on and so forth. Also create timestamp and other kinds of things, put it on the blockchain. That's one idea we've seen. Again, some variations of this where you are not only detecting exact location, but also keeping a buffer so that you can document before or after or bigger window and so on and so forth. And you will see many examples of this in terms of patent or literature. But what typical scenario in real world example is that videos are not used as they are. Where once you create a video and once you publish a video, there are a lot of transformation going on. And one transformation that is most important in our view is redaction. That means at body cam, let's take body cam as an example. In body cam, once you take a picture, you want to take off the faces and all other personal sensitive data and still be able to say whether this is an authentic body cam from officer number 23 on a particular day in New York City or not. That's the question. So it's not just like previously I mentioned, just the whole video as it is, exact copy, putting a hash of that into the blockchain is a good first step, but it's not enough. Many times you want to have redaction capability. By redaction, I mean the published counterpart of the video is edited in some legitimate way, because you can't always show the faces of the victims, faces of the police officer, faces of the other bystanders, and so on and so forth. If you have removed some of these sensitive information and still be able to say that this is an authentic video, it will be quite useful. And there is again, unfortunately or fortunately, because that is also an opportunity for innovation. How do you efficiently do integrity of video after redaction? That's one of the major problems, and we'll show you one example where I'll skip this. Again, what is done for video also has been done for audio. Again, take a hash, put it on a blockchain. That's all people have done, and it's not very useful. So this is the basic one problem, right? You can come up with your own sets of problems, but one problem people have not worked on is that after you redact the portions of the video legitimately, can you still say that this is a legitimate video or not? And again, many variations of this exist, like if it is scaled, if it is rotated, if it is some geometric transform is done, is it still authentic video or not? Nobody has done it, because just taking a hash of it, as you all know, just changing one pixel would change the hash value. So it hasn't been done for any realistic sense. So one, maybe a couple of patents around this, what people have done is that, they will run some ImageNet object detector or something like that to get all the objects in the video, and then they will systematically catalog them if they want to remove some of these pieces, right, some of the faces, etc., they will just say that, this mask, this mask, this mask. So let me go slowly. Let's say that we have 10 frames, and in 10 frames, let's take MS Coco, roughly 7 objects are there per frame or something like that. So those are all detected using your favorite object detector, and then each of these object detector will give you a mask related to what objects it has been detected. And they created a hash for that particular mask. So now you can create a redacted video for, say that I want to remove mask number 23, 77, and 55. I don't want to be included. Then I can create another hash of the entire video by saying exclude portion these 3 masks in that. So it is where computer vision and blockchain meet together to say what portion of the video should not be considered in creating a hash. But still it is very coarse, not very practical, because as you all know, object detectors are not perfect. So sometimes you may not be able to eliminate all the faces. So now people are thinking of putting a manual process inside so that you can have a manual process of putting the masks and so on and so forth. But they're all, in our opinion, they are all very kludgy. They are not solving the real practical problem, because a typical problem in this world is that an officer generates 8 hours of body cam video a day, right? And if you add number of officers, number of police departments, you can't do this manually. You need to have a very robust, scalable solution. I don't think such a solution exists. And again, opportunity for all of us to innovate. I won't go into much detail of this, but any questions on the content management? The third portion is related to the inference management, and this is where we are talking about the models themselves. That you hacked, you learned a particular model, and you want to trade that model with somebody else. You don't want to trade that model. You don't want that model to be abused. How are you going to create a marketplace around that using blockchain? Because now you want to say proof of ownership. I own this model. Nobody can use this model. If somebody used the model, I want to know it. Somebody wants to hack this model, I want to know who hacked the model, and so on and so forth. So there are many, many emerging requirements coming around where the distributed ledger can be used to both protect and collaborate legitimately and detect when these models have been illegitimately used. So that's the third place where blockchain will be increasingly used. And again, we haven't seen huge amount of work here. We'll share in our PDF the bibliography of the literature search that we have done, but we haven't found much work here. So typically, this is one of the motivations of why this model marketplace is very useful, is because, each individual stakeholder, in this case, it is a hospital. Each hospital has bunch of sensitive data, and they want to build a particular disease model or a drug model, whether drug efficacy model, and so on and so forth. But they all have limited data, and by many laws and regulations, they cannot share. They don't want to share. They don't want to compromise their sensitive part of their data with their colleagues. Or they just want to, they think that they are the owners and they should get most benefit out of it. So is it possible using distributed ledger to federate all this data and make a best model out of it, and all of them can share without sharing the sensitive data? That's one problem. And again, in the bibliography, you will see a couple of papers related to this. But people have done, I'll summarize it in a slide or so. not much work is done here. There are basically three approaches people have done. One is the, some mighty central server where everybody sends their data. They assume that the central server is not going to be compromised and is very trusted, and you can trust the owner and access to that, and it will run latest and greatest machine learning frameworks, and then send back the model back to each one of the participants. The second one is that each of the parties don't really send the data, but they just are running their own model on their limited data, and they're only going to ship the gradients back to the central server, and the central server is going to do the learning based on that gradients, and then send back the weights back to each of the parties. And then, of course, the most distributed version of that is that everybody sends everybody else their gradients, and they can do whatever they want and learn the best possible model they all can. All of these models basically are assuming is that everybody is curious and honest. What if I am just a malicious party? I don't have any data at all. I just want to participate so that I can get as much data as possible from the other stakeholders. So there are many, many scenarios where adversaries can today take advantage of these federated models, whether it is fully centralized or fully decentralized. And how do you actually prevent adversaries from taking advantage of the other honest workers, and how blockchain can be used to deter and detect all of these adversarial problems where there is not central trust into anybody. That's the kind of the basic question. And again, not much work has been done beyond maybe you will see about a dozen papers around this, no more than that. The second problem is that once somebody attacks, their model becomes better, and then they can start attacking other models, and then therefore they becomes more and more powerful. So attacks in computer vision world are they start a vicious circle, because once you start finding how to leak into get the information leakage, you can amplify that by using a lot of machine learning frameworks. So yeah, so in that sense, how can you detect and early report, share the suspicious incidents? And this is where we believe the blockchain, just like the identity management, where we know where the sources of attacks are coming from. Can you do a lot of mining around these records and figure out who are the malicious and who are the benevolent parties? So to summarize, what in the inference management space is that it's a very, very hard problem. If somebody can solve it, we don't know. But what we feel is that the current solutions that are there are around, either federating the data, that means everybody sends data to some central authority or each other, or sharing the models themselves, and whether to share or not share is basically based on the trust. Can you trust or not trust? The other approach has been, whitening. That means you intentionally add noise to your data or models and share it, and then the issues related to those are basically, because you're adding noise, you are not really optimally sharing all the data. You may be unintentionally disclosing, you may be saying that, I want to, the length of nose is related to, incidence of Parkinson's disease, so I don't want to share that. But what if the flatness of ears is also related, that you may not know? So there may be some unintentional disclosure of sensitive data that you don't know. And then whatever data is shared, people can use a lot of mining techniques and so on and so forth. So it's a whole can of worms, but looking at it positively, there is a lot of opportunity how distributed ledger can be used to both detect and deter and still effectively collaborate. Lastly, this is my favorite part in terms of physical world where, not just identities, but physical world where the distributed ledger can be used. And basically whatever is happening in the real world because of the sensors and because camera is the de facto sensor these days, can you reflect that back into the blockchain? And the basic research issues are related to the integrity of the whole infrastructure, the sensors to the processing communication, everywhere the integrity, privacy, and obviously scalability, because the amount of data that is going around in terms of videos is the dominating content on the internet right now. So the first use case is related to the surveillance. As you know, with the progress in the machine learning and computer vision, almost all videos coming from static cameras or moving cameras can be analyzed and detect what are the objects, what is the foreground, background. You can do what are the attributes, and so on and so forth. So the modeling has gone to such an extent that each one of these attributes you can easily ledger them, put in the what can be put in the central ledger can be also put in distributed ledger. But we have a lot of experience in terms of the surveillance in cities, for example. The number of events in a typical busy city camera is over 1 million events in a day. How do you actually store them all and be able to ledger them scalably is not clear, and that's where I think is one of the biggest challenges is going to come in terms of surveillance. The second big idea we believe is that related to the satellite imaging. As you all know, the satellite imaging technology is improving every day. What was available 10, 15 meter pixel resolution now is available in centimeters, 30 centimeters, even 6 centimeters. So a lot of things that could have been done on a ground camera can be now done using satellite imagery. And huge number of applications are mushrooming around what physical reality you want to analyze out of the satellite imagery, right? And it could be usage. I'll give you a very funny incident. People want to analyze the number of cars in particular companies' parking lot to tell whether they are going to do better or worse on the next stock quarter. And that can be done based on satellite imagery today because of the resolution that is possible. So huge number of features can be done. Usage is, that is, number of parked cars is basically telling you how many employees are there, how many customers are there, and so on and so forth statistically, and can be used to gauge the business of a particular business entity. Condition like pipes, whether there is a leakage in oil pipes, by that I mean natural gas lines and not, whether something needs repair, so on and so forth. And it is giving, so this middle layer is all about what kind of features that you can extract, and then this layer is all about applications in various domains, like you can tell, for example, the trains are so long, you can tell which trains are running on the schedule. Based on just satellite data, you can tell which trains are going on schedule and which aren't, and so on and so forth. So erosion of the ocean lines and so on and so forth. So given this broad range of analytics one could do on physical environments, what can be done to not trust a central authority, right? Because now you want to say what kind of uh, gas leakage is going on a pipeline. Now, if I'm a malicious entity, I could create any amount of hoax, just like a fake news. I can create any number of artificial events. How do I make sure that what is there in the blockchain is an authentic reflection of what actually happened in real physical world? Again, using a lot of consensus, incenting people like us, developer community, which can say, oh, 20 people saw that there is a, 20 people means not with their visual eyes, but they saw by their analytic engines that there was a leakage, a telltale signs of leakage from satellite image from a particular gas line at a particular longitude, latitude. That could be a reliable way to say that, oh, indeed there is a leakage, and that is more trustworthy, and it is a distributed, so nobody can tamper with it. It is immutable, and therefore it can be, the beginning of the next generation of infrastructure and applications and so on. So that's another opportunity which is we believe is waiting to be tapped. This comes up a lot in terms of our own lot of experience we have in terms of supply chain. Lot of enterprise customers, right? They want to model their entire where their supply comes from. To share very interesting anecdote about Walmart, the reason why Walmart prices are the lowest, this is from nothing private information, this is from one of their books they wrote, is because they model their supply chain to the last mile, and therefore they can tell where I can get my next acquisitions, purchase of my goods cheapest from somebody. But in the process, you also want to know that, especially food related items, you want to know whether the food is not contaminated, nobody tampered with it, or there is no spoilage, because when I'm using trucks from Arkansas to New York, the air conditioning for the milk was not at the right age, or not milk. Milk is probably mostly local, but let's say cheese or something like that. They didn't use enough lower temperature in their storage. So by the time it went from Arkansas to New York, the food went bad. So all of this you can track, because blockchain is a way to track the provenance and integrity. You have the sensors, you have the on the truck, and you have the cameras. You can track these and create a irrefutable proof of where this food came from, who all have handled it, who, if there was any evidence of tamper, who had the opportunity to do it. All of this is worth a lot of money to a lot of enterprises. So again, blockchain is being considered as one of the places where all of this infrastructure conditions could be reflected. This is another interesting use case. Again, this is just a tip of the iceberg, but a lot of the similar cases come like this. As you know, diamonds are kind of the illegal currency for a lot of people who are doing illegitimate business, and maybe they, like Karthik was saying, use bitcoins, but a lot of them also use just diamonds as a way of doing the transactions. And tracking these diamonds is not easy, because the diamonds are diamonds. Anybody will take them and then use that for encashing and use it as basically money. But one of the use cases that we came across was that if you image these diamonds with really highest possible resolution, then very small microscopic defects these diamonds have can tell the identity of the diamond. And that can let you track which diamond went from where to where to where. And there is lot of interest in tracking diamonds on blockchain because this is using this kind of analytics because people want to know. Because if you can track the flow of diamonds, you can also track how you have some chance of knowing how the illegal business is going and so on and so forth. But the defects of diamonds is just the tip of the iceberg, like I said. Lot of other defects and inspections of infrastructures and items can be similarly be documented on blockchain credibly and irrefutably, and that could be another opportunity for innovation. Traffic, again, this is coming from a paper that was published very recently that the CAN bus is the kind of the bus that is inside every vehicle which collects lot of these data. It is, you can't see because of the low resolution here, but when did I brake, when did I accelerate, when did I turn, when did I put indicator signal. And on autonomous vehicles, you can do even more than that. Yeah, all analytics that started one particular decision and so on and so forth. And how do you share all of these data with various stakeholders, right? The car manufacturers want to know, if there is a incident, insurance companies want to know, and so on and so forth. And how do I share a lot of this data with all of these stakeholders for general benefit of the car industry, but also my benefit as a driver. I want to know something goes bad in my car. I want to know the best. But at the same time, I don't want to disclose where all I am going or anything private data that I don't want to disclose because the increasingly cameras may be fitted inside my car and so on and so forth. So again, blockchain is a way of sharing legitimate data among legitimate stakeholders without compromising the sensitive data or anything that I don't want to share. And like Karthik was mentioning, you can write all of these contracts, smart contracts, on what can be shared with whom, what are the situations where a particular transmission of data to a particular stakeholder is fine, can be written out and spelled out as a smart contract. And therefore, this is just a white paper. Nobody has done any real work on this. But again, for budding entrepreneurs that may be in the audience, this is another, a good topic for marrying blockchain and computer vision. Similarly, the automotive security, when to apply, this is kind of extension of the previous one, but more relevant in terms of automotives, especially self-driving automotives. When do you apply remote updates or remote software updates into a car? That's a big ecosystem that is going to grow where, some remote developer community will be able to update a car remotely through the wireless. How do you write a smart contract between what the car driver wants and what the developer community has? There has to be, very complicated, sophisticated contract, and we suspect that a lot of this will depend upon various analytics, how many times car did what, and suspect that which is related to the lidar on the car or the various sensors on the car, including cameras, and again opportunity for computer vision systems, computer vision developers and researchers to contribute. This is a very recent paper. Again, it's still on archive, not published, but drones are becoming very popular, and then how do you, because these drones are very short-lived, right? Many people don't know this, but the most drones that are within the reach of applications, they have very short time flight, less than 30 minutes, about hour, and but one could use a lot of them and